So linear algebra is exactly that, algebra with lines. Okay, now we are mostly used to lines in two-dimensional spaces. But you could connect the corner of this desk to the corner of this desk with a straight line, and it would be a line in 3 dimensions. And you could have technically lines in 4 dimensions, 5 dimensions, and so on. So we call spaces that can have lines linear spaces. And we are going to look at mathematics surrounding what can happen when we have lines more than just in 2 dimensions. The first thing that we start off with is a review of systems of equations from grade 10 and grade 11. So you've learned y equals mx plus b. That's the one that you remember the most. You could always rearrange y equals mx plus b to be in this form, ax plus by plus c equals 0. That is called the general form. And in the general form, you can make the general form so there's no fractions. And you can make the general form so that whatever's in front of x is positive. So they sort of have, well, here's the general form. Get rid of your fractions, move things over, have a positive. That way everybody can look at it the same way. When you have a system of linear equations, and usually what you solved up till now was 2 equations with 2 unknowns, okay? So you have a certain number of equations and a certain number of unknowns. And then you attempt to solve them. So some things that we have solved in the past are 2 equations with 2 unknowns. And the techniques that you learned in the past were substitution. That's probably the most common technique, the go-to technique. And then you also learned an elimination technique. So we'll review those quickly right now. The substitution technique was based on the idea that if you could get one of the variables easily by itself, then you could substitute what it was equal to into the other equation. So for example, oh, there's no equation here. Does yours have an equation? Does it equal 1 on yours, or is it equal 0? 0. Okay. Just wondered. Okay. So if we look at this, and often with systems of equations, we even like say this is equation 1, this is equation 2. It's really easy to get x by itself in equation 1. That would be the easiest thing to isolate. I can do that by just subtracting the 4y on the other side. Then I can substitute. Now, a common silly mistake with substitution is someone takes that x and substitutes it into the same equation they started with. And if you do that, you'll find out fascinating things like 6 is equal to 6, and 4 is equal to 4, and 2 equals 2. And you find all sorts of things that are true that you probably knew already. Like, guess what number 7 is equal to? 7. But if you substitute it into the other equation, so I'm now going to substitute into equation 2, well, where the x was, I can now write 6 minus 4y minus 3y plus 1 equals 0. Now I have an equation where I can solve for y. And in doing so, I get 12 minus 8y minus 3y plus 1 equals 0. 13, if I move this to the other side, is equal to 11y, and so y is 13 over 11. And once you have solved for y, then it allows you to go back and solve for x. And when finding x, you could plug the y value either into equation 1 now or into equation 2. Some students like to plug it into both to make sure that it works. Some students are like, no, I'm confident that I know what I'm doing. I'm going to just solve for it into one. So we've got this already isolated. 6 minus 4 times y. And 66 minus 52 would be 14 over 11. And we often write a systems of equation solution as a coordinate or a point. So in this case, we found our x coordinate to be 14 over 11, our y coordinate to be 13 over 11. And what's actually happening with that point is that equation 1 is a line. Equation 2 is a line. If you have two lines, most likely they're going to cross somewhere. Sometimes they don't. Sometimes they're parallel and they never cross each other. But randomly picking two numbers everywhere most likely will cause those two lines to have different slopes, and they will cross, and that point where they cross is the solution. So that's why we often write the solution as a point, because we're representing that those two lines cross at that point, and that point is the only point that makes both equation 1 and equation 2 true. There's lots of points that make equation 1 true, right? We can find a whole bunch of points that make x plus 4y, like, ooh, x is 2, y is 1, that makes 6. But 2 and 1 won't make the second equation. So this, I would say, is probably the most common technique for solving a system of equation. You substitute in, right? The elimination technique, what it does is it says, can you get a coefficient either in front of x or in front of y? And I like to say the same, but one is positive, one is negative. So for example, can you see that right now the coefficients in front of x are not the same, the coefficients in front of y are not the same. But if I took equation 1 and I multiplied that whole equation by a negative 2, multiply the left side by negative 2, the right side by negative 2, do you see that equation 1 would become negative 2x minus 8y equals negative 12. And equation 2 is still 2x minus 3y. And in the elimination technique, another thing that you'll do is make sure that all of your values line up in columns. So my x column first, my y column, I moved the 1 over so my constants were in the same column as well. What that allows you to do is if these are the same number, but one's positive and one's negative, you can add your two equations together. The idea being is that if this side is equal to negative 12 and this side is equal to negative 1, if I add the sides together, they should still be equal. And what's really nice here is this just becomes 0, this becomes negative 11y, this is negative 13, and now you have an equation just with y. You divide both sides by negative 11, the negatives would simplify, and we get 13 over 11 again. Then from here, you would do the same thing. Once you get y, you plug it into either equation 1 or equation 2, and solve for x. Sometimes the elimination technique is really nice, because look how much less math it felt like we had to do. Something canceled out right away. So substitution is used more, because substitution technically always works. Like in some of the equations that we did in calculus, where you had to get x by itself, you got like 100, you had x times y in a volume question or an area question. So it made sense to isolate a value, because you weren't dealing with two lines. You had like a parabola and a line. So things don't cancel out nicely. But the elimination technique works really nice if you have two lines. All right, there. This is it rewritten with the actual equals here. Okay, so as said before, when we're solving a system of linear equations, we're looking for that point of intersection. And if we categorize them, there are three types. The most common is the independent solution. You have two different lines with two different slopes. Those lines have to intersect at one and only one point. So you have different slopes. They could have the same y-intercept. I guess technically we can put a line through this. Because you could have two lines with the same y-intercept, and that just happens to be where they cross. It is important that they have different slopes. Secondly, we have a dependent system, which is the exact same line. And if you think you have one line, and then you draw the exact same line over top of it and ask, how many times does it intersect? Can you find a point on both of those lines and they're the same line? You'd be like, well, every single point is on both lines because they're the same line. So we say this has an infinite amount of solutions. The two equations are the same line. Why does this happen? And you're like, well, this seems kind of silly. Wouldn't you notice right away? But I could write the line in different forms. One could be in the y equals mx plus b, and the other one in ax plus by plus c equals 0, and you don't notice right away that they are the same. So these ones are exactly the same. They will have the same slope, same y-intercept. Okay? And then finally, we have an incompatible system where there are no solutions. Why are there no solutions? Well, those lines are parallel. They have the same slope, different y-intercept. They will never cross. Oh, you can also solve things if you want to use Desmos or graphing calculator. You could type them in and then find out where they intersect. So graphing, I would say, is only helpful if you're using technology. Sometimes you can solve something with graphing, but then you only find the solution if it works out at a nice point. The first one that we did with 13 over 11 and 14 over 11, if you graph that, you'd be like, oh crap. They like intersect somewhere in the square, but it's not a nice point. So now my graphing solution isn't very helpful. So if things are nicely lined up, I like to use elimination. And looking at things here, you choose a variable to eliminate. So I might look at the x's and go, oh, I could cancel out the x's really easily if I multiplied equation 1 by 2. Because then I'd have a 2x and a negative 2x. So I multiply equation 1 by 2, and I get 2x minus 4y equals negative 2. And I take my second equation, which was negative 2x plus 4y equals 2, and I add them together. And I get the following. 0 plus 0 equals 0. And you start to feel, did I do something wrong? No. What we have here is, by the way, just to make sure, I hope you know that this is always true. 0 equals 0. That is true. And if it's always true, this is the idea here that we have infinite solutions. this is an example where we have two lines.
Interruption. Could all three teams who are running for student council please report to the office? That's the three teams that are running for student council for next year. Please report to the office.
These are the same line, right? If you wanted to rearrange these into y equals mx plus b, you would really see that, right? If I wanted to get y by itself here, I could move the 2y to one side and the 1 to the other. You get 2y equals x plus 1. Divide everything by 2, and you would get 1/2 x plus 1/2. And in the second one, if I have the 4y by itself, I'd move the 2x over, 2x plus 2. Divide everything by 4, I get 2 over 4, which reduces to 1/2, plus 2 over 4, which reduces to 1/2. And we notice that these two equations, if the question started that way, you'd be like, oh, I don't have to do anything. I can see that they're the same. But the question started in a way that it wasn't super easy to see right at the beginning that they were the same thing. So you use a solving technique, and you get something that's always true. Okay? Elimination is nice this way, because if you made that substitution error where you substitute into the same equation, you might think, oh, they're the same line, but you made a mistake in the technique of substitution. So that can be a danger if you use substitution wrong. So we want this one to be two lines that has no solution. In other words, right, this tells us they have to be parallel, but not the same. So what could be ways that we could go about doing this? Couple of things. One, we could rearrange this so that you have y equals mx plus b, because if they're parallel, that means the slopes are the same. So if I rearrange equation 1 and equation 2, start with equation 1 here, I can move the x over, divide everything by k, that would be equation 1's y equals mx plus b. Equation 2, I can move the kx over, and now equation 2 is equal to y equals mx plus b4. If they are parallel, this value and this value has to be the same. So we can write that negative k has to equal negative 1 over k, and we can solve for k. Multiply both sides by a negative k, you'll get k squared equals 1, square root both sides. K is going to equal plus or minus 1. And one thing that I would do to check is that if you plugged in k, do you still have different y-intercepts? So I would look at this value here. If you plug in 1, my y-intercept is 2, this y-intercept is 4. They have different y-intercepts, so they're parallel and not the same line. Same thing with negative 1, I plug in negative 1. Here we have negative 2. Here we have 4, right? So this question, the way that it's worded right now, fairly straightforward, not really tricky. If I wanted to make it tricky, I could have made this number a 2, and then only one of the answers would have worked, not the other. So, we solve for k, they would have no solution. an equation and it has fractions. As much as I would love you to be experts in working with fractions all the time, one of the greatest skills in working with fractions is how to get rid of them. It's like, it's almost hypocritical as a math teacher. I want you to work well with fractions. So the first thing we're going to do is get rid of them to make our life easy. But it's true. What I would do in this first equation is I would not want that 2 on the bottom, not want that 3 on the bottom. How could I do that? Well, I could multiply everything by 2 and get rid of the 2 on the bottom here. And I could multiply everything by 3 and get rid of the 3 on the bottom. Okay? So sometimes people multiply things by 6. Okay? I don't mind doing it systematically. We're going to take this term and multiply it by 2, this term and multiply it by 2, and this and multiply it by 2. And notice that would simplify here. Technically, okay, by now you've done lots of equations that when you multiply one side, you just multiply every term on that side. You know that. Technically, what you're doing is you're putting brackets around this left-hand side and multiplying it by 2 once. But if there was brackets around the left-hand side and you multiplied it by 2 once, you could distribute. That's why every term gets multiplied by that number. Okay? Next, I'm going to multiply every term by 3. This one by 3, this one by 3, this one by 3. And notice that would cancel out here the fractions. And my first equation is now, distribute this, 3x minus 3 plus, distribute the 2 there, 2y plus 4 equals 6 times 4, 24. And I could simplify this to just be 3x plus 2y, put my like terms together, 23. And now that my fractions are gone, oh, you see how elimination is going to work out beautifully right away, okay? Notice that the y's are already matched up, okay? So don't just go into elimination saying, oh, well, I need to make my x's the same. I always cancel out my x's first. Look at both equations. This is our new equation 1. Here's our equation 2. I'm going to write it right underneath it. It's already x minus 2y equals 5. We can add those equations right away. And x is equal to 7. Once we find x is equal to 7, we can plug that in either into equation 1 or equation 2. I would probably plug it into equation 2 just because I'm having troubles writing letters. And again, you could type this into decimals as a quick way to check your answer, right? Beautiful that we have technology that allows us to find the answers right away. Now, before we get to the next one, I just want to show you, because we used elimination and saw what happened when there was infinite solutions. We did have a question with no solution, but it was solving for k, a little bit different. And we're quite familiar with
Sorry for the interruption.
what
Would
one
all
answer
grade
looks like.
11 students, along with their teachers, please head to the gym now. That's all grade 11 students, as well as their teachers, please head to the gym now.
So I'm going to just do another example here. And one equation is going to be 4x minus 2y equals 3. And the other equation is going to be 2x minus y is equal to 8. And so you're going to solve this equation. You're thinking elimination. You've got your two equations, equation 1 and equation 2. You go, oh, I could eliminate my x's quite easily if I multiplied equation 2 by a negative 2. And sometimes I always like to get the coefficients the same but a different sign. Sometimes people like to get just multiply equation 2 by 2 and subtract instead of add. Okay? You will find you make more mistakes subtracting than you do adding. So that's why I sort of recommend multiplying by a negative here. So I'm going to rewrite equation 1 is 4x minus 2y equals 3. That's my equation 1. And my equation 2 is now negative 4x plus 2y equals negative 16. I add them together and I get 0 plus 0 equals negative 13. And you're like, wow, I think I've discovered something new mathematically. 0 and minus 13 are the same. No. Okay? You are wrong. That is not true ever. 0 is not equal to negative 13. In which case, when this happens, this is what it looks like when you get no solution and you're solving. You get something that can't possibly be right. Everything else cancels out, and you're like, yeah, 0 is minus 13. Right? So if everything cancels out and you get 0 equals 0 or 5 equals 5, that's always true. That means they were the same line. But if everything cancels out and you get something like 0 equals negative 13, that's never true. This doesn't always happen, but when you were in grade 10 or 11, did you solve systems of 3 equations and 3 unknowns, or did you just stop with 2 equations and 2 unknowns? Do you remember doing ones like, no? Okay. So we are going to do the same thing that we did with elimination. With elimination, what you did is you got rid of either the x or the y, and then you could solve for y. When you have 3 equations, equation 1, equation 2, and equation 3, what you can try to do is you can try to eliminate one variable twice, then you get 2 equations with 2 unknowns, and do it again until you finally get something you can solve. So it's the same process, just takes longer. Okay? So we've got 3 equations, and you could look at them and think elimination, because there's multiple ways of doing this equation, and ask yourself, what would you like to eliminate first? What looks like it's the easiest to eliminate? And there'll be different perspectives on this, okay? I look at my variables, x's are like 1s and 2s, y's are 2, 3, and 5. So first of all, x's is nicer than y's. And now here would be an argument. Z is 3 and 5, and 1's already eliminated. So some would argue, I want to eliminate z's because I only have to do that one more time. And some would argue, no, the numbers still are not very nice with the z's. I'll still want to just eliminate my x's. Okay? So in this situation, I'm going to eliminate the x's because usually when you get 3 equations with 3 unknowns, there would still be a z in the third one as well. So what does it look like? Okay? First, And I'm writing this out so that we have it. Sometimes the plan is to create two new equations, eliminating x, and then you have two new equations with just y and just z. Okay? I really like equation 1 and equation 2 as my first one to choose. I choose equation 1 and 2, and you can eliminate x with 1 and 2, 1 and 3, or 2 and 3. There's three different choices you have for picking two equations and eliminating x. So this also can be different depending on someone's choices. I'm choosing 1 and 2 because they work out really nicely right from the beginning. This is 0. Negative 2y plus 3y is y. 3z plus nothing is still 3z. And 9 plus a negative 4 is 5. And I am going to call this equation A. I like to use numbers for the first time I go through things, letters for the second. So there's equation A. Okay? I'm also going to choose another one to eliminate. I'm going to use equation 2 and equation 3, and I'm going to multiply equation 2 by 2. So equation 2 is now negative 2x plus 6y equals negative 8. And I'll just rewrite equation 3, 2x minus 5y plus 5z equals 17. Again, my x's nicely eliminate. That was my plan. And I'm going to get y plus 5z equals 9. That's my new equation B. What we've done by choosing to eliminate one variable in two different ways is we created equation A and B are now two equations with two unknowns. What can you do with this? Well, I would probably take equation A and multiply it by a negative 1. Some people who are comfortable would just say, I'm going to just subtract instead of add them. And that's perfectly fine. So if I take equation A, which is now negative y minus 3z equals negative 5, and equation B is y plus 5z equals 9, and I add those together, I get 0 plus 2z equals 4, and we've calculated z is 2. Now we just need to work backwards. If you know that z is 2, you could plug that back into either equation A or B and figure out what y is, right? If I plug it in right here, y plus 5 times 2 equals 9. So I'm plugging it in to equation B. I get y is equal to negative 1. And then you've got z, you've got y. Now you can go to any of your first three equations and plug those in. So I'm going to go to, I like equation 1 because the equation 1 just had an x. And it had minus 2 times y, where I plug in the negative 1. And it had plus 3 times z, and I'll plug in the 2, and it was equal to 9. Combine your like terms, and you get x is equal to 1. So our solution is 1, comma, negative 1, comma, 2. Right? is X, this is Y, this is Z. And what we actually had in our first set of equations, when you have an X, a Y, and a Z, is we actually have a line in 3 dimensions. One day, before I retire, no, it's not gonna happen. But I imagine a 3-dimensional smartboard where I can just pick a point here and draw it over to here, and you would see this laser beam in the air. And then I'd say, this is our second line that goes from here to here, and our third line that goes from here to here. And all 3 of those lines happen to intersect perfectly at this point. Do you know how to draw lines in 3 dimensions on a 2-dimensional piece of paper? Have you ever had to do that before? Okay, so what you do is normally we draw with a y-axis, right, and an x-axis. So you imagine taking that x-axis and y-axis like it's on a piece of paper, and you are drawing a 3-dimensional picture. Okay? How do you draw a 3-dimensional picture? Like, you imagine taking that. Wait for it. 3-dimensional. Here we go. I'm imagining taking that piece of paper and putting it on this table. There we go. Now it's. Yeah, all right. Poor Rohan, not going to art school. Now I'm telling him to draw pictures. So I'm just giving you the visualization of a table, because if you took a piece of paper that had your x and y axes on it and put it on the table, do you see that your y axis and x axis would look like this on that table? There's still a 90-degree angle here, but when you draw it in 3 dimensions and bend, it's not actually 90 degrees anymore. But you're imagining it in 3 dimensions, so you can, like, you measure that, that's not 90 degrees that I just drew. But in your head, you can see it in 3 dimensions. I've taken the piece of paper, and I have drawn my x here, my y there, and it's now in 3 dimensions. And in 3 dimensions, I could draw something straight up and down, and that would be my z-axis. So here is a 3-dimensional attempt to draw, and we are going to draw the point 1, negative 1, 2 on here. Would you agree that the 1 would be 1 in the x direction, the negative 1 would be negative 1 in the y direction, and the 2 would be 2 up in the z direction? So first of all, if you just had to plug in the x and the y part, and I'll underline that in purple, if you just were drawing this point, and it was on your piece of paper that was on the table, do you see that that point would be right there? 1 to the right and 1 down. That's where it would show up on your paper. Where does the 2 come in? Well, the 2 would be going up 2 units. Okay? This is going up 2 units right from there. I'm going to take those dotted lines and put them there. And technically, that is the point 1, negative 1, 2 in 3 dimensions. I think seeing the purple lines there help you visualize that in 3 dimensions, that it's actually gone up 2 units from that point there. And we could draw lines in 3 dimensions. We're not going to draw all 3 lines now. We don't have, 20 minutes to just have fun drawing lines, but we could, right? What would you need to draw the other 3 lines? You just need 1 other point, and then you just have to connect the dots in 3 dimensions, right? Oh. Can you, here, should we find our let's find one. This one's really easy. Let's find our let's find our x-intercept of line number 2. Line number 2, if you find your x-intercept, that would be plugging in 0 for y, you would get x equals 4. And since there's no z, that means z can be any. But you do have, can you see that on this one right here, you have the point 4, 0. If I go to my graph, where is 4, 0? 1, 2, 3, 4. That would be this point right there. I know that it has to go through there. So that would be a 3-dimensional line drawn on a 2-dimensional surface of your piece of paper. But linear spaces doesn't stop at 3 dimensions. We go into 4-dimensional questions and 5-dimensional questions and stuff like that, which this already on a piece of paper, that's why I'm like, wouldn't it be so nice? Because if I had this axis in 3 dimensions, I could just grab this point here and touch this point here and drag, oh, it'd be like a mathematical dance. I could just like move all over the place and connect lines. You're drawing them?
Yeah, I'm trying.
Mm-hmm. Is that in decimals?
No, this one is you, just one of them.
Okay. And it's actually drawing the planes, right?
Kind of.
Yeah. So what happens in, like in 2-dimensional spaces, we actually have a line. In 3-dimensional spaces, it's actually what you're drawing is a piece of paper in 3-dimensional spaces that goes in all directions. So these 3 equations are actually like 3 pieces of paper going in all directions, and they intersect at this one point. Okay, that's too much visualizing for the day. Here is a problem-solving question for you. What the heck? How much, they all hopped on there at the same time. How much do they weigh? Take out a piece of scrap paper, or grab one from the scrap paper bin, or draw it anywhere on yours. I would like you to solve it in 2 different ways, and define one way as easy and one way as not hard, but long. It's almost. Ooh. Maybe it will come in my lifetime. Roham's found a way to take a picture with his phone and superimpose a 3-dimensional rotating object on it.
Especially for the sleep.
Yeah. I tried this morning, it didn't come up with something good. I opened up ChatGPT and I said, I'm tired, can you teach my math class? And it said, but it was too much work to tell it what to do. question. Do you see a dog with a collar or a dog with its head chopped off? Perspective. Now, are you using X, Y, and Z, or are you using C, D, and now? Did you go B and bunny, or R and rabbit? Anybody go H for hare? Just wondering. Or did you see them as certain kinds? Right? Is that a B for bulldog? The cat looks like a Burmese and a bunny, so you used capital B, little b, and beta.
Why the dog? Why?
If you figured out two different ways to solve this, then you can go on to the worksheet. Oh, I'm still recording here. May as well stop it. Oh, but I'll pause it. Or no, should I not give the answer on the video? Oh. I'll pause it. So there are the equations, and yes, you have a system of 3 equations. Elimination works really nice to get it down to 2 equations, so you could use the technique that we just did to do that, and it works out nicely. However, we could also do this with a little bit of strategy and shortcut, which is like substitution and elimination in some ways. But what I'm going to do to start with is I'm going to take the 3 that I know, and I'm going to imagine that these are actually twins. So I actually have 2 cats available, 2 bunnies available, and 2 headless dogs. Okay? And I'm going to move them, I'm going to take these 2 and move them onto this scale. And I'm going to take these 2 and move them onto this scale. What is that scale going to say? It's going to say 54 kilograms. Can you see it? If I move these ones onto here, because they're twins, and these ones onto here and they're twins, I would have 2 dogs, 2 cats, and 2 bunnies on a scale that says 54. Right? I eat one of them each for lunch, and I'm left with only half, giving me 27 there. Right? Then once I figured out that 27, I could be like, oh, if I take off these 2, that's taking off 20. That means Mr. Cat is 7. And if I take off The dog and the cat, well, that leaves little bunny is 3. And if I take off the cat and the bunny, that leaves the dog as 17. And kind of a neat way of looking at this same question, thinking outside the box. So yes, we have a system of equation, but sometimes you can fiddle with that systems of equation to make it work out. What I see more typical in a question like this is we could even do it with, like, sometimes the numbers are that actually solving for the cat and the bunny and the dog separately are all terrible numbers. But the question's final answer is nice.